Yes, definitely.
So you're all welcome to this morning's session. Before we start in earnest, Thanasi has something to tell us about tonight's activities. Please.
Yeah, so
Thank you. So now we can start this morning's session. And the first speaker is Susanne Reffert, who will tell us about new developments in the large expansion. Please.
Thank you very much. So it's great to be here. My first in-person conference in a long time now. So the first time I see at least part of my audience faces. So yes, I'm going to tell you about new developments in the large charge expansion. This is by now based on a whole series of papers, but I have to be very brief and just concentrate on a few aspects today because I have just half an hour. This work has been done with also quite a list of collaborators of mine, many of whom are in my group in Bern, but yeah, you see there are people all over the world that we've been working with. So what's the motivation? As you all know, strongly coupled physics is a difficult topic. We can't do the perturbative expansion, which is really what we know how to do best. And even our most basic intuition about field theory is perturbative. So that's a problem, but of course we have symmetries. So what people usually do is they try to make use of the symmetries of the system as much as possible and also look at some special limits or subsectors where things simplify, which is also what I'm doing here. I'll be studying theories which have some global symmetry. And if I have a global symmetry, I can decompose my Hilbert space into sectors of the charge under the symmetry. And if I focus on subsectors where the charge is very large, I can in fact use this charge as a controlling parameter. So I'm back to being able to writing expansions. I'll be focusing mostly, but not only on CFDs, which of course, I don't think I need to go into detail here. It's very important in theoretical physics. We all know the important properties of CFDs, but not having intrinsic scales, many of those are strongly coupled. And in 2D, of course, we're in pretty good shape still. We can use the conformal bootstrap in bigger than 2 dimensions, or we can directly work on the lattice. But these are theories that are really very good candidates for this large charge approach that I want to introduce today. So, quick overview. I'll be explaining this large charge approach in the case of the O2 model, which is really the simplest model you can think of for that. I'll go through that with you, and then I will generalize that to the O2n vector model, where I will just be very brief on the finite n results. I'll say a few words about the large n limit, and once I'm at large n and large charge, I can actually go away from the conformal point. I have a lot of control there. And yes, it will be time to end by then. So the O2 model, I'll try to be brief. So in the UV, you simply have a complex scalar and the phi to the 4 interaction. But for now, I won't care about the UV. What I care about is that this model is known to flow to a fixed point in 3 dimensions, to the Wilson-Fisher fixed point. And that's where I want to describe my theory at large charge. So I assume that also in the infrared, I still have a complex scalar. And for my convenience, you see this is the infrared field, which is different from the UV field. I will just write this as a radial and an angular degree of freedom. This has also the advantage that the global symmetry is manifest. I can shift the phase chi by a constant. Now I'll be considering this theory in a box, mostly on a 2-sphere because I want to use state operator. So I have one scale of the manifold where I work on, and by fixing the charge, I give a second scale to this problem. So I will study the CFD in a sector between 1 over r, where r is the scale of my manifold, lambda is the cutoff of my theory, then I have here the charge density, and this is much smaller than here the UV scale. Now, I want to write an effective action in the Wilsonian sense in the infrared. For now, I assume that the radial degree of freedom has a large VEF, and I write my action like this. I have here my kinetic term for the radial part, and from this I can read off, I'm in 3 dimensions, phi has the mass dimension 1/2, which tells me directly that I must have an a to the 6th term in the potential. On top of this, of course, I have the kinetic term for chi, and I have the coupling to the curvature, which is here, the conformal coupling, really. I have 2-dimensional constants, and this is my starting point for my linear sigma model. Sorry, this was constructed to be scale invariant here at 3 level, and I just do the semi-classical analysis. I solve the equations of motion at fixed charge, and in the case of the O2 model, there must be homogeneous. The lowest solution, the lowest energy solution is homogeneous in space. Now, the charge density is given in terms of this expression here, and the lowest energy solution is the one where A has a VEF that is constant. Chi also gets a VEF, but it is, as you see, a non-constant VEF. It's mu t, that's the ground state solution. And now I have to actually determine this VEF here. That determines my mu, sorry. And I can do this by minimizing the classical potential. These were the 2 terms of before, but from charge fixing, I get this other term here, which results in a centrifugal barrier. So my classical potential has this shape here, which means the minimum is not down here because of this contribution here, but somewhere away. In fact, this VEF, when minimized, goes like charge to the 1/4. So if I choose a large charge, this assumption I made of having a large VEF for A is obviously borne out. Mu scales like charge density to the 1/2. I can calculate the energy of this ground state. I found just to the Legendre transform to get the Hamiltonian. And I find this formula here where I have two dimensionless parameters that were related to the ones I had in my action. Here I have the volume and the curvature appearing. That depends on what manifold I work on. And these two parameters here, these coefficients, I cannot calculate them within the EFT. These are just Wilsonian coefficients for me. Later we will see that at large n I can actually calculate those. But here within the EFT, I can't do that. And then the scaling at leading order, it goes like q to the 3/2. The next curvature term is q to the 1/2. And everything else already is suppressed by negative powers of the large charge. Now this classical solution is the vacuum around which I study the quantum theory. And so I put the fluctuations on top here, A hat and chi hat. And it turns out that A itself is a massive mode. So if I'm truly interested just in the low energy theory, I would want to get rid of this mode here. Chi, on the other hand, we expect to be a goldstone. We'll see this is actually the case. Because fixing the ground state breaks symmetries, I started with the full conformal group and the O2 or U1 symmetry. Then the boosts are broken by charge fixing. And in the end, the O2 gets broken to this helical symmetry, which is a time translation minus U times the generator of my U1. So from here, I would expect one goldstone just from the breaking of this O2 here. Now I want to integrate out A, the massive mode. So at first approximation, if we're leading order, I can just eliminate A via the equations of motion. And I find a nonlinear sigma model action that is where the dynamics is described entirely by the phase chi, by our goldstone here. Of course, this thing I could have just guessed by dimensional analysis. Chi is a phase and dimensionless, so this is something of dimension 2. I need to get to dimension 3, right? So this I could have just done like this. In fact, I want to go a bit further. I don't go into details here because my time is short, but if I put together dimensional analysis, so just looking at dimension 3 operators and making sure everything is parity invariant and conformally invariant, I find still infinitely many operators that fulfill these conditions here. It's a Wilsonian action. But now I can use the fact that I have large charge. Now I will use the scaling with respect to the charge density to determine which of these infinitely many operators are not suppressed. For this, I need to know that del chi goes like rho to the 1/2, whereas higher derivatives of chi have a negative rho scaling. And the solution is this thing here, where the first operator is the one we already had seen at leading order, and then we have a coupling to the curvature, and everything else will be suppressed. This term by itself is scale invariant, but not conformally invariant, but it has a friend that is suppressed that forms a conformally invariant combination. I have again, of course, these dimensions parameters, my Wilsonian coefficients. And yeah, as I said, everything else is suppressed. So that is my nonlinear sigma model. So maybe keep this in mind because we will see that again later on. In case you're concerned about these fractional powers here, don't worry because we always have to understand this as an expansion around the ground state. We always expand around mu t plus fluctuation. In fact, let's do that. Let's expand it around the ground state to second order, and we see that's what we get. So we get something very large that comes from the classical ground state itself, and we get this guy here from the goldstone. And from this we use to compute the zeros of the inverse propagator to get the dispersion relation for chi hat. And we find that it goes like p, so like we would expect a goldstone to go, but the speed of sound is 1/2 of 2. In general dimensions, it would be 1 over square root d, and this is directly dictated by conformal invariance. That's universal. So we see indeed chi is a goldstone of type 1, which means the relativistic type. What about the quantum effects? Are they also controlled? And the answer is, except for the Casimir energy of the goldstone, yes, they are all suppressed. So let's evaluate the Casimir energy using the standard techniques. With the zeta function regularization, we find this number here. So now we're ready to actually calculate stuff. Let's calculate observables, which in the case of a CFD means the so-called CFD data. If we have all the scaling dimensions of the operators plus a fusion of 3-point function coefficients, we can calculate any endpoint function, so that's enough. So let's do that. I show the scaling dimension, and for this I use the so-called state operator correspondence of CFD, which states that if I work here in R to the D, I can get the scaling dimension or conformal dimension of an operator inserted here from calculating the energy of a state that lives on the cylinder. So what we've just done was calculating the energy of the ground state, which thanks to the correspondence gives me for free the scaling dimension of the lowest operator of charge Q. So that's the formula for my scaling dimension. Here I have the classical ground state energy that I've shown plus the Casimir energy. And this is the result. So this is the classical contribution, that's the Casimir contribution. 3-point function coefficients have been done by Ratazzi et al. For the O2 model. So very good. That's our prediction for the O2 model at large charge. And we've seen that I can summarize the effective theory at large charge by vacuum, which gives the biggest contribution, the goldstone, and everything else is suppressed. So that came out pretty simple for a strongly coupled model that we didn't really know what to do with at all before trying at large charge. So let's test the prediction, right? That was the formula that we had, and we got people who work on the lattice to simulate that. And that's what they got. This curve is this curve here. These are the data points that they have. And these horizontal bars are error bars that are so small that they basically look collapsed onto each other. So we see, yes, this really works very well. They got up to charge 11, which is not a very large charge, but on the lattice, it actually is the best one could do. And what is striking is, well, first of all, here on the lattice, of course, I can calculate. I do a 2-parameter fit, and I get values for these coefficients that I couldn't calculate in the EFT. And strikingly, this keeps working for small charge. And of course, the question is why. I'm not going to say much about this. Later on, Johannes is going to give a talk where I think he'll get back to that a little bit. So we see it works really well for O2. Where else might it work? So let's go beyond now. Let's go beyond the O2 model, and the most obvious generalization, if we stay in 3 dimensions, is to go from O2 to O2n. Now we have a non-abelian global symmetry group, not just the U1, but we have this O2n symmetry, and this gives rise to new effects, which I will just summarize here because of short time. One important point is that now different symmetry breaking patterns are possible. Before I just had basically my U1 that I broke down to nothing, right? But in particular, one can find inhomogeneous ground state, but there's still the homogeneous case, which is the simplest one, where the ground state has the same form. We get again this mu t for the chi's, and the interesting part is that we just get 1 mu for all the fields that we can rotate. The symmetry breaking pattern for the homogeneous case is the following, where the global symmetry gets broken down from a un to a un minus 1. which means that we expect 2n-1 Goldstone degrees of freedom by the usual counting. But here something new happens. We have this Goldstone of the O2, this relativistic one or type 2 one with the 1 over square root of 2 dispersion relation. But now we find a new sector where we find n-1 non-relativistic or type 2 Goldstones, which have a different quadratic dispersion relation. Okay? And they also count differently. They count twice. So we have twice this plus one of those, which gives us the right number as expected. So this is new and a bit different from what we used to. It turns out that the ground state energy at the order we're looking at is only determined by the one conformal Goldstone that we already had in O2. So the formula looks the same thing, just the same. Here the coefficients, of course, they depend on the n here. But this guy here, the Casimir energy, just comes from the one relativistic Goldstone. So this is universal for any n here. And was also verified independently, numerically. And to make sure everything's fine, we went back to the lattice friends and they simulated the first non-trivial non-abelian case, namely the O4 model. And you see it again matches very well with different values, of course, for the two C coefficients. Good, so that's all fine, but like an obvious next thing to do, you have the O to n, is to take the large n limit, right? This will give us extra control. So we can do that. Here we don't need to take recourse to the EFT. We can really start from first principles, expand the path integral around the saddle point, and at leading order we find it solvable, and we get the exact same powers for the scaling dimension too. Q to the 3/2, Q to the 1/2. So everything is as expected. You have to go to the next to leading order in n to also reproduce these dispersion relations of the Goldstones, which we did, and it's fine. But we can do more than that, of course, because we have now an extra control parameter. We have Q, but we have also n, so we can go beyond what we learned from the EFT. And one thing we can do here is to calculate these coefficients, C. At leading order in n, that's the solution what we find. We see that the C 3/2 goes like 1 over square root n, the C 1/2 goes like square root of n. And okay, we have this lattice data for O4, which is clearly not at all large n, but it's still within 10%. So even at very small n, that works out nicely. And our friends went to somewhat larger n. This is C 3/2 on the lattice, C 1/2. And you see, it looks plausibly well, right? Now, since we have n, we can also take the other limit. We can work in the limit of Q over n being small. And here we see that actually, what is this operator of the lowest operator of charge Q? That's simply phi to the Q. And we can find the scaling dimension. And here, as expected, in the small charge limit, delta Q goes like Q, and which is exactly here. If I write delta over Q, this is exactly the engineering dimension of phi. And you can do a calculation perturbative with around the zero charge vacuum, and you find this contribution from the tree level and this one at one loop. So this matches up also in the small charge limit. Now we can do even more, and we can try to interpolate between these two regimes of small q and large q using methods of resurgence, which I again will refrain from mentioning because at 11:30 there's going to be a talk just about that. Now let's do something else. Let's try to go away from the conformal point. Nothing in the idea of the large charge expansion is really tied to the notion of conformality. It's just simpler because we have all this extra space-time symmetry which helps us constrain the operators in the EFT, etc. We can use state operator and so on, so it's convenient, but it shouldn't be necessary. So let's try to go away. And in the ultraviolet, now we're back in the ultraviolet, in the O2N model, this looks like this. Here we have the kinetic term, then we have the quadratic term and the quartic term. And we know that if we set R to the conformal coupling, that's the Ricci curvature, so that's 0 in flat space, this model flows to the Wilson-Fisher fixed point before we just cared about that. And at the fixed point, this coupling U here goes to infinity. But we don't want to go all the way there now. We keep U finite. So we're not at the conformal point any longer. And now we invoke all the large N machinery. So first of all, we need to fix the charge, which means we have to add a chemical potential. And we perform a Slattanov transform, which gives us a new field lambda, which started its life as a Lagrange multiplier. So after the Slattanov transform, our action looks like this, where D is the covariant derivative that contains the chemical potential. And now we see if we look at phi just appears quadratically. So we have this new field lambda. Because of the chemical potential, lambda gets a VEV, which we call m squared. This is the chemical potential in the 0 direction, where the m appears. So it's actually this VEV for lambda that gives us some extra structure to work with, because otherwise, if I integrate out phi, I lost most of the structure. But fixing the charge gives us extra structure, and that allows us to do all the stuff that I'm going to do now. So let's integrate out the phi, and to leading order in n, this leaves us with this expression here, where we have zeta of -1/2 on the manifold. So that's also what we have at the conformal point, but away from the conformal point, we have this extra contribution here with the R and the U. And if I work in flat space, which is what I'm going to do from now on, this simplifies to this expression here. So I have a very simple expression. And since M minimizes the field, if I now put del mu chi for m square, I put that in here, you remember, hopefully now, that I get exactly back the nonlinear sigma model we've seen already in the O2 model. This here is the del mu chi to the 3/2 term. And this is new, this we didn't have before because we had U equals infinity, okay? To make this more transparent, let's try to extract the effective potential, going to the linear sigma model, which has this general form where capital phi is the VEV of the radial mode of my field, and m is the VEV of the angular mode, and that's the effective potential. I write the equations of motion for the radial mode, and plugging back the solution, we must recover here the nonlinear sigma model, as we should. But looking better at these two equations, we make an interesting observation. These two together define a Legendre transform. So this is nothing but the Legendre transform of V in the variable phi squared. We have to pay attention to convexity though, so we will use the more general definition of the Legendre transform involving the supremum here. Applied to our case, V, the effective potential, is given as the supremum over m square phi square minus L, and written out, that's what I get. This is my eta here. This is my full effective potential. And now I have to look at three cases, depending on the value of R here. R bigger than 0 looks like this, where here the dashed line is just the tree-level potential of before, and the red line is this guy here. And here it's quadratic in the field, okay? This is the unbroken phase. Then we have also the critical point. Again, 3-level potential and V, but for R equals 0. This is the conformal case. So here this is a lot flatter, you see. In fact, this is a sextic potential, like we've seen in the linear sigma model of the O2 model. This goes like 5 to the 6th at the origin. And the most interesting case is R smaller than 0. You see, if you have this negative, what happens? You get the Higgs potential, Mexican half potential, whatever you want to call it. Clearly, that's the broken phase. You have spontaneous symmetry breaking taking place. And we know in the books it always says that, well, of course, the real effective potential is always convex. Quantum effects make it convex, okay? Right. But here I don't need to wave hands. This is an actual function that I plotted here. It goes like this V here. Once I'm away from the minima, this is the location of the two minima. And in between, the supremum just makes it flat. Okay, so I really get, without waving hands and saying quantum effect, I can calculate this full effective potential. This is unpublished work that should be out fairly soon. My time is basically up, so let me just flash the free energy at the critical point. This was actually an older result already, which I can get by taking the Legendre transform of L, not with respect to m squared, but m. This is again always convex thanks to the supremum. And as you've seen, I didn't need to calculate lots of infinitely many Feynman diagrams to get there. But using the interplay of large Q and large N, this was something very, very straightforward. So this made life easy for us. So yeah, my time is up. So I showed you the O to N model, the finite N result. We've seen the agreement with the lattice results. And we've seen that we can even, at large N, calculate these coefficients, flow away from the conformal point, and find the full effective potential. Now I have some short Q&A, which I'm going to jump through because I want to end on the further directions, because today I really just picked out one facet of the large charge expansion. So there's work being done on supersymmetric models. There's the connection to holography, where it's also unpublished work in both cases that we heard about at the conference. So there should be a lot of interesting new stuff soon. One can look at operators with spin. You can compare to the Bootstrap. You can look at more stuff on the lattice. People are working on CFD in other dimensions as well. People have looked at Chern-Simons, matter theories. Then you can do just like we did large N 4 minus epsilon for extra control. You can go away from the conformal point. There's also quite a big story with so-called non-relativistic CFDs, which are just models with Schrödinger symmetry, non-relativistic ones, where you can also apply large charge. And recently there's been some work on boundary CFDs. Even the relation to the weak gravity conjecture has cropped up. And of course, there's the whole thing of fermionic theories, where there's been some first attempts as well. And it would be very interesting, of course, to apply the large charge expansion to the case of QCD. With this, I'm done, and thank you for your attention.
Very nice talk. And are there any questions from the audience here? One.
Hi. Hi, thanks for the very nice talk. So it seems to me that the two-dimensional case requires a very different approach qualitatively.
You're very right, because yes, I mean, first of all, in 2 dimensions, you can solve certain things. So you can really explicitly go to the large charge sector. And then there's the whole issue with goldstones. Are there goldstones? Are there no goldstones? Coleman says there are no goldstones in 2 dimensions, right? But then there was a paper by Nicolis that explained us that we still have boost goldstones in 2D. And boosts are broken at fixed charge. So there is still stuff to work with, but that's stuff that, yeah, there's been a bit in the paper of the Stony Brook people. Let me see. Doesn't go back anymore. Sorry. Homogeneous et al. In short. And we're actually also looking at 2D cases. So some things you can really, right here, this paper I was referring to. So they did some stuff in 2D. And we're also working at this. So it works differently, but it still works, yes.
Reconstruct almost universal large charge expansion and things like that.
You can, right, I mean, you can take, for example, you can do stuff really explicitly in some solvable theories, where you write a partition function and you pick out a fixed charge sector, and you can really write it.
Very interesting. Thank you.
Niels?
Thanks for a nice talk. You mentioned that you could check some of these results using the conformal bootstrap. Can you give an example of such?
So the conformal bootstrap, that was, sorry, it goes back. Here, here Jafferis and Zhiboydov did some work on that. And it seemed to me like it was really, really hard. But they could reproduce what we found in a much simpler way. So I think it's not the most convenient way of doing it. And then no one else has done it since, which probably for really technical difficulty involved in that.
If there are no further questions from this audience, maybe we should check the online audience. No questions. So then we thank again. introduction. No worries. So next speaker is Niels Obers, who will tell us about, as far as I can see, TBA, but you may have changed your title.
Yes, okay. So I'm going to be talking about an actual title, Torsional Newton-Cartan Geometry for Non-Relativistic Strings. Let me first thank the organizers a lot for bringing us together in one room again. It has been fantastic. The work has been done sort of in a series of papers actually over the last 5 years. And it's going to be mainly focusing on this last paper. And you can see the collaborators. And I should also maybe advertise that there will be 3 nice talks on Friday by Roseel and Landsteiner and Bergshoef that are closely related. So this is going to be a talk about non-relativistic physics. So it's kind of interesting to maybe take a helicopter perspective and see sort of the overall framework in which you should see this talk. I will come with further motivations soon. This is a very nice cube of the cube of physical theories. It's also called the Bronstein cube, which I actually like to also present to my students in various classes to sort of show where they are in their education. You probably have seen it. If you arrange using the fundamental constants of nature, h bar, g Newton, and 1 over the speed of light, frameworks of theories in a cube, then you recognize your classical mechanics, special relativity, GR, and okay, I will not go through the whole cube, but obviously what we're interested in, many people here, and that's also the theme of this workshop, is to understand a theory of relativistic quantum gravity. And many people here do think that one of the leading approaches there is string theory. But if you actually think about it, the way we approach this ultimate holy grail is most often from either the QFT side or the GR side. We either think like, we know how to deal with relativistic quantum field theories. Let's turn on, G. Let's turn on gravity. Or going from bottom to up, we have a classical theory of general relativity, and now we want to quantize this. But if you actually study this cube a little bit more, you see here, okay, I write here NRG. Some people would maybe say, why don't you write just Newtonian physics there? Actually, one of the things that has become clear over the last 5 years is that this is actually richer than just Newtonian physics, because there's a framework that actually is still non-relativistic, but includes strong gravitational fields. And then going up, there's a corner that you could call non-relativistic quantum gravity. And so the punchline is here that there is sort of a third route through which you could approach quantum gravity coming from this side. Now, of course, that should presuppose that you understand what I like to call this 7th corner of the Bronstein cube, because that's already a corner of some type of quantum gravity, but without relativistic effects. But yeah, so and for this, you should also understand this better. But so this way of thinking, first of all, poses the question: is there something like a non-relativistic quantum gravity, and does string theory have a role to play there? And I think we're learning certainly that the answer is yes, and that's where non-relativistic string theory comes in. I should also maybe say, but I don't have time to talk about that in this half an hour talk. This also sort of strongly suggests that, say, we all know holography, that's a duality between this corner and this corner. So this also strongly suggests that there are avatars of holography by taking a non-relativistic limit that relate these corners. And actually we have some, just starting with the ADS CFT as we know it, some examples of that. Now, that's a central tool that has been essential in the last years understanding better non-relativistic physics, and that has been sort of the return, because it's not completely new, but the return of what I call non-Lorentzian geometries. So there's recent progress in understanding these non-relativistic corners, both in gravity, quantum field theory, and string theory, really builds on an improved understanding of non-relativistic geometries. Non-Lorentzian geometries. What do I mean with that? There are many examples of that, but as a sort of a one-liner, these are spacetimes that have local symmetries other than Lorentz. That's why we call them non-Lorentzian symmetry geometries. So you again think that's sort of a very wide negating arena. So it's pretty much everything else than pseudo-Riemannian geometry. But you know, there are some sort of concrete examples of this that, you know, where the local symmetries are not Lorentz but Galilean, and typically when you have Galilean, then you get something very specific that's known as Neutrikatan geometry. But more generally, you can think of other type of local symmetries. Actually, these non-Lorentzian geometries appear really in a wide variety of area and have been examined like that since 2013. So this is just to give you, before I go to the details, sorry about that, little overview without references, you can find them. But so they appear as boundary geometries in non-ADS geometry. They appear in covariant formulations of the post-Newtonian approximation of GR. Also in covariant formulations of, you know, non-relativistic hydrodynamics, of which there are many types. They go under the name now of non-Lorentzian fluids, and obviously they have potential applications in condensed matter systems. They appear in Horava-Lipschitz gravity and also non-relativistic versions of Chern-Simons and JT gravity. Interesting connections with double field theory also exist, and you will actually see in some of the more technical part of the talk tantalizing incarnation of that. They appear in near BPS limits of you know, vanilla ADS CFT, and they appear in non-relativistic limits of string theory, and that's the main part of this talk. Again, why non-relativistic string theory? Why could you be interested? I give you some reasons. Some of them I already said, but just to re-emphasize again, it could be, no, but a simpler UV complete theory of gravity. Just as relativistic string theory makes contact with gravity and so Einstein gravity and corrections through the beta functions, non-relativistic string theory makes contact with non-relativistic gravity theories at low energies. That's also interesting. As this already mentioned, related to limits of ADS CFT. And more generally, it's a very rich, it appears to be a very rich limit of string theory, and poses sort of the larger question: what is the landscape of non-relativistic string theories? Now, non-relativistic strings are actually not novel. I mean, what's novel is the recent developments in the curved target space formulation. But for there's a cohort of young people here that maybe were not around in the early 2000s, but there's also a cohort that were around. And they might very well remember the good old days when we were looking at various limits of string theory and cos theory. Anybody who here remembers theory? Very few, but yeah. So, and in this whole development of looking at various limits of string theory, actually Gomis and Oguri in 2000, and also Danielson and company constructed non-relativistic strings on flat spacetime. The emphasis is on flat spacetime, but they already found various interesting results. But for some reason, the question was never asked: what is their, curved target space generalization? Just like we know the Polyakov action for relativistic strings. And what's becoming clear now is that this target space for this flat non-relativistic string theory developed by Gomis and Oguri is a type of Neutrikatan geometry. I will briefly explain to you what Neutrikatan in its original form is very soon. And in view of the time also, there have been various developments on this target space formulation that I mentioned here. But sort of the punchline, sort of the technical part of this talk is that there were various issues with previous formulations, such as overparameterization of fields, such as maybe overly constraining with so-called torsion constraints. The details are not so important. Overly constraining the target space and some other technical things. But long story short, I want to briefly revisit in this talk the formulation of non-relativistic string theories and their target space geometries. And actually, that's the punchline is, and probably you appreciate the punchline better when you know what Neutrikatan geometry for particles is, because now we're doing it for strings, and I will review that after this punchline. But the punchline is that we find a formulation in which the target space geometry of non-relativistic strings consists of some metric data, but included in the geometry is a two-form field that has a very physical interpretation. It couples to the tension current of a massive or tension-full non-relativistic string. We'll see shortly, this is in complete analogy with a non-relativistic particle that also has a mass current. And there also the geometry, then in that case, includes a one-form field that couples to the mass current. And then you might say, okay, this sounds very familiar because string theory has some kind of two-form, right? The B field. But here, for the non-relativistic string, well, just like the B field for the Polyakov action is part of the generalized geometry, here this two-form is also part of the type of generalized geometry. And so this is very much in parallel with the non-relativistic particle that I will discuss. It follows from two procedures. There are actually two very generally interesting ways to get non-relativistic theories. One is you take a theory and you null reduce, and the other is, so you go one dimension lower. The other is you are in a given dimension and you take the large speed of light limit. And it's a nice consistency check that they both give the same result. And then, okay, this is maybe for aficionados, but I find it very beautiful. This geometry that you find, it arises from the gauging of a novel non-relativistic algebra that we dub the F-string Galilei algebra, which actually, in the same way that pseudo-Riemannian geometry can be seen as obtainable from the gauging of Poincare. So this F-string Galilei algebra is actually a certain Inoue-Wigner contraction. The Inoue-Wigner has to do with taking a non-relativistic limit of not just the Poincare algebra, but the Poincare algebra extended with the symmetries of the B field. And here, double field theory, people also see some overlaps, like before taking the limit. How am I doing on time?
10 minutes left coming up.
10 minutes left coming. Okay, that's so. I'll not give the outline actually and just delve into it. For people that don't know Newton-Cartan geometry, remember just one punchline. What assuming local Lorentz gives pseudo-Riemannian geometry. What Cartan realized, in Newtonian gravity, there's no local Lorentz symmetry, but local Galilean. If you make that local, then you get a geometry known as Newton-Cartan. Using that geometry, he could geometrize the Poisson equation. So, so Einstein really did two of these things, right? He geometrized gravity, but then he also implied his equivalence principle. There are other ways to geometrize gravity using other local principles, and that's what Cartan showed. Give you an impression of TNC geometry. So one way to see the geometric fields is by thinking about the most general form of a null, of a Lorentzian metric with a null isometry. So that would include a time-like field bind, a degenerate metric on spatial slices, and a one-form field. This is a way to think about Neutrikatan geometry. So instead of a metric, these are the metric data. So time and space is separated. Also, of course, you also have to understand what are the local symmetries. These transform, they are tensors under diffeomorphisms, because we still have diffeomorphism invariance, but they transform in a certain way now, not on the local Lorentz, but on our local Galilean boost. And that's given here. And using these metric data, you can build the whole geometry. You can build the analog of a Christoffel connection and Riemann curvatures, etc., and construct action. So remember that as a punchline. That's Neutrikatan geometry. I say right away, it's also very natural that this M field appears as part of the geometry. Think about if you couple relativistic field theories to a background, you would couple it to a metric. Varying the response to varying the metric gives the energy momentum tensor. Here, because in a non-relativistic theory, mass and energy are not the same anymore. The variation with respect to this time-like field bind will give the energy current. The variation of a quantum field theory coupling to this M field will give the mass current, and mass is not equal to energy anymore. And so one way to think about Neutrikatan geometry is sort of spatial slices and time evolving. And what's very important is that whereas in Neutrikatan geometry, as it was introduced in the 20s by Cartan, he insisted on this time-like field bind to be exact, because in Newtonian physics, time is absolute. What we realized in a series of papers, it's sort of trivial, but that's it sort of was implied also by holography, that you don't need to assume that it's exact. There's you can have causality with tau mu being hypersurface orthogonal, and that's goes beyond absolute time. Yeah, so you can ask now, what is the action of a non-relativistic particle coupling to Neutrikatan geometry? In view of the time, I will, because I went a little bit slow in the beginning, I will be a little bit quick. I mean, the upshot is that the action takes this form, and there are different ways to do it. You can get this action by a null reduction of a massless relativistic particle in one dimension. You can also get it by taking a charged extremal particle in the same dimension and then taking a large C limit. And the action is given here, contains a kinetic term, nicely covariant. So this is, yeah, it also looks like a nice non-relativistic kinetic term, and a potential term that encodes the coupling of the mass current, as I said, to this one form potential. And it shows, by the way, as you see here also, that the zero component of M is like the Newtonian potential, and that's part of the geometry. And as the Groningen group showed, sorry, this is actually 2012, because this was an important paper many years ago. They showed that you can get this geometry from gauging the Barkman algebra, which is the centrally extended Galilean algebra. I emphasize you can also get this, so you can do a null reduction of a massless relativistic particle. You can also get it as a C to infinity limit, but then you have to start with a massive, extremely charged action. So I choose MC squared, and then you take a limit. This is not so important, but you get the same action. Now, and it's this procedure that we would like to mimic for the relativistic string. And the relativistic string is totally primed for this, because the relativistic string is actually extremely charged, right? It carries extremal charge under the B field. Because, you know, in the Polyakov action, the tension is the charge is the tension in terms of in front of the B field. Let's take a step back. We want to understand the underlying group. Thanks. We want to understand the underlying Lie algebra structure of the Neveu-Schwarz sector. And you know, by the way, so this is closely related to the spirit of double field theory. There were also some earlier papers that we found that addressed this, but it's quite neat, I think. I never really realized it. If you look at now I'm ignoring the dilaton. It would be interesting to understand the dilaton, and maybe somebody in the audience knows this. So I'm now still doing first relativistic string theory. But you know, if you ask yourself the question, I have a metric and a B field, like in string theory, and you know they transform like this on the diffeomorphisms and gauge field transformations. Can you find a Lie algebra valued connection that reproduces these symmetry transformations? You know, we of course know how to get this, right? That's you can get it from a Lie algebra valued connection on the Poincare group. But so this you can get by extending Poincare with an extra translational operator. I call it Q. You know, so the field line of P is E, the field line of Q is pi. We all know how to construct G, right? That's EE, the field line squared. But if you take this translational generator and construct the B field like this anti-symmetrized product of E and pi, you can show that the group transformations generate this gauge transformation. So that was our starting point, because now we want to take this and take a non-relativistic limit of the coupling of a relativistic string to a G and a B field, taking into account that that they have this substructure, that there's this substructure in the fields. So we take the action, now we go to Western-Witten. Okay, how do we do the non-relativistic limit for string theory? We take the field line, so we have the E field line and the pi field line, right? That was related to the B field. We make a so-called longitudinal transverse split. Capital instance is longitudinal and the other one's transverse. And then you know you let this go like with C. So this is the analog, like for a particle, the non-relativistic limit is like open up the light cone, but for a particle, you know, the wall sheet, well, there's a walled line. Here, the light cone opens up on the walled sheet. So that's why you have a vector of C here. Okay, now it's various technicalities, but you plug this in, you take the limit. There's an important cancellation of a divergent term, also for the non-relativistic point particle. That happens because the string is extremal, and that really happens because the tension here is the tension here. We all know that, right? It's not arbitrarily charged. And at the end of the day, you get an action that looks very nicely similar to the one of a non-relativistic point particle, depending on this transverse metric. Before, like for the particle case, we had a tau mu, but now there's a tau mu for every longitudinal direction. So there's a tau mu 0 and a tau mu 1. And the B field that was there to start with has morphed into what we call an M field that plays a completely analogous role to the one form potential in ordinary Newton-Cartan geometry. And why? Because you can precisely see here that M couples to the walled sheet tension current of this massive non-relativistic string. It also actually shows that non-relativistic strings obey some type of weak equivalence principle, because if you would compute the equations of motions, you can see that the gravitational mass is equal, the gravitational tension of the string is equal to the inertial tension. Okay, now this actually has some rather non-trivial symmetries. It has immediately obvious invariant on the gauge symmetries of this two-form Neutrikatan field. But it also has a rather non-trivial symmetry that sort of flips. Thanks a lot. That interchanges this term and this term, and it's actually that's the analog of boosts. So as a non-trivial symmetry, stringent and Galilean boost, you can check it that this action is invariant on it. And that's actually the string analog of the symmetries of the point particle. But you can ask, what is the underlying symmetry algebra? So now that's quite easy to obtain because you take the symmetry algebra of the Neveu-Schwarz sector of the relativistic string, but now with the B field included. So it's Poincare plus these extra translational operators. You decompose that into longitudinal and transverse. There's some names. And then, okay, so you do some basis transformation. That's very often in non-relativistic limits. And you take the C going to infinity limit, which in algebra terms means a Nono-Wigner contraction. And you get a certain algebra that I gave the main commutators of the main non-trivial ones. Rather non-trivial commutator between stringy boosts and the wall sheet Hamiltonian. Also stringy boost in the transverse translations, etc. But but this really, so I use this very nicely, I think, some kind of generalized geometry approach to the relativistic string, and then takes a limit of that. This is to say you get the same result by null reduction. So just a nice consistency check, but I will not give details. So before I go to some open problems and what this opens the road for, I just want to emphasize, because various people are confused, and maybe we were confused at some point, that when you look at getting non-relativistic theories from relativistic parent theories, there's actually sort of two viewpoints, and they're both equally interesting and equally useful, but they shouldn't be confused. One is, and they have some different features. One, and okay, it goes with the unoriginal name of type 1, but okay, you have to find some name, thanks. It's you really take the theory and you send C going to infinity. You don't do an expansion for large C, but you send it to infinity. That requires then really canceling divergent terms. And that's the approach I took in this talk. The other is you take a theory and you do a large C expansion. Then actually each term in the action would generate more and more fields. And we have done it, for example, for GR, and recently has been done by these people for the string. So yeah, I just want to emphasize these two viewpoints. And there is some kind of non-zero overlap between them, but they're not the same. And they also come with different type of geometric constraints that I just flash on this transparency. So let's get to the outlook. Now, once you have a nice covariant wall sheet action with a target space time of the type also that we got here, and it has, of course, the same question has been asked before for the other target space formulations, as I tell you here. But it will be interesting with this new view on the target space geometry of non-relativistic strings to obtain the beta functions and effective space-time actions. I say there are already recent results on the other formulations, but it would be interesting to put all the dots on the I there. This is my last transparency. As I mentioned throughout the talk, it would also be interesting to include the dilaton in this analysis. And maybe actually even before doing the limit, if there's anybody in the audience that knows sort of how should I, I call it string Poincare, so Poincare plus translations. What should I add to also have the dilaton in relativistic string theory? If somebody knows this from somewhere in the literature, let me know. The Hamiltonian analysis would be interesting. There was a recent paper by Susanne doing that for our new formulation, and we're also working on it. Then there's the whole universe of open strings and branes. various interesting works have been done on DBI actions, Gomis and Jan Yu. Also from the double field theory point of view, quite interesting papers on D and M branes. We're also looking at it. And I think this is more than academic. I think it will, well, for me, it's quite important. Will be kind of important to get the supersymmetric generalizations and understand RR fields. Thanks. I'll stop here.
Okay, Niels, very much for your good talk. And are there any questions in the audience here?
Thank you, Niels. My question is about, you mentioned very briefly that you have these two approaches: either you brutally send C to infinity, or you consider the large C expansion, and then you get extra terms which have inside extra fields.
Yeah.
Can you say a few words more on how these fields appear, or how they could appear nevertheless in the brutal C goes to infinity limit if I don't know what you can do?
So maybe I should. So your question is, let me understand what the connection is between the fields that appear in the strict C to infinity limit and the ones in the expansion. Yes. Okay, so it's nicely illustrated maybe with this table. And actually, let's not complicate things. So let's go to the particle case. With particle, I mean GR. So there, if you take type 1, again, it's a really boring terminology, but if you take the strict limit, what you get is really what's known as type 1 torsion Newton-Cartan geometry with these fields. It's basically what Cartan introduced and then allowing for torsion. But also, it's also the torsion constraints that's sort of important, because if you couple this to, you can couple this to a particle, and I really highlighted how you could get the action. But that coupling can be done for any of such geometries. You don't need any conditions on tau. You don't need any foliation conditions. Now, here, let's jump to the particle type 2. And you get this. Then the leading order field actually is tau mu. So it's just a subset of this field. Next to leading order, then you start including these fields that you had before. But with a slight subtle difference that it's the same names, but they transform slightly different. Because actually the algebras that you here get for the aficionados are obtainable by so-called Lie algebra expansions. And you cannot get the Barkman algebra from a Lie algebra expansion. So, and the next to leading order, it's the phi and the B field. So, long story short, they have an overlap, but the transformations are actually subtly different. But they overlap again when you take a subset of fields and take absolute time. We can talk more about it. Thank you.
There's no questions. Down there are two questions, actually. Down there. First one.
How should I think of a non-relativistic winding mode, or equivalently, like T-duality will start this non-relativistic limit? Or?
Okay, good question. A very important question, and in half an hour is very little. You cannot do justice. So, start with the last part of the question. There are various versions of T-duality that have been examined. So there's still T-dualities, and then sort of a difference between longitudinal T-dualities, or T-dualities in the direction of this wall sheet, and transfers. With the winding modes, actually very important, and I didn't mention sort of the physical states. And if you look at the Oguri paper, so just for the strings on flat space-time, which would be, it's not flat Minkowski space-time, right? But it's the flat version of the space-time I just presented. There actually, the states need to have a non-trivial winding to be physical. So there's always a winding around the longitudinal direction. So there's always a compact direction in these non-relativistic strings with a non-zero winding. what's very beautiful and what Gomes and Oguri showed, many people don't appreciate it. I think it's now really beautiful. They looked at the tachyonic 4-point amplitude of such mass winding states that have some mass, and they could show that to leading order, this Veneziano-like amplitude of these winding states shows that these massive winding modes interact with the Newtonian potential. So, so you can, well, maybe not surprising, if you can get GI, you should also get Newton, but they showed it very beautifully.
Okay, we're running late. Can we just have one more question, please? Maybe Thomas?
Just quickly then, you mentioned the problem of coupling to the dilaton, but just to make sure, you see the dilaton in your string spectrum, is that correct? Because for the normal string, you have the dilaton.
No, okay, good question, because not really. I mean, they're not matched as fields. So that's a little bit more subtle, but a good question, and I'm sure there are more questions we can talk in the break.
Okay, then I think we have to look at the online, if there are any online questions. No? Then we thank Niels once more.
Sorry?
I have slides.
Can you send it to the profile?
I did. There's some idiotic name. It has CFU in it. Yesterday night. Ruben, David Ruben.
Yeah.
Okay, so we move on to Ruben Minasian, who will tell us about higher derivative couplings in string theory, F theory, at order alpha prime theory.
Thank you. And I joined the previous speakers in thanking the organizers. It's nice in many ways to be here. So I'll be talking about work which I had been doing with Jim Liu for years, and also some work in progress with Jim and also Raffaele Savelli and Andreas Schaffner. I should start from apologies. There are no other credits on these transparencies, but I will be very happy to provide references. I should also start with a convention that kind of the mentioning of generalized geometry are mostly gratuitous and more intended to be as a teaser to this audience. If you wish, the non-understanding or understanding of higher derivative couplings is one of the unfulfilled promises of generalized geometry. When this was a new and promising subject, it seemed like a good taste that every speaker would finish the talk promising that next they will say something interesting about higher derivative couplings. Well, we are still waiting. So, from quantum gravity point of view, in these couplings, be it a genus expansion or alpha prime expansion, and I'll be talking about lower forms of life for both, are somehow stringy probes of the geometry. So this is our timid steps going out of supergravity. I mean, it's a very old subject. Since I will be talking only about alpha prime cubes, so the first corrections in type 2 theories, and I will be only talking about 8 derivatives, so the first allowed terms. And, you know, if this includes things like Green-Schwarz terms. So this is the beginning of string theory. And somehow these terms, people have been returning to them in many, many ways. I mean, they spread off lots of different activities, going to more derivatives, higher orders in alpha prime. There is a huge literature on this. There is very interesting kind of number theoretic developments. Recently, the R to the 4 started coming up even in Bootstrap context. So one area which is relatively unpopular and unexplored is really going nonlinear. So not adding derivatives, but going beyond 4-point functions. Okay. You may ask why. And why hasn't it been done until now? Okay, it hasn't been done until now because it's not a particularly pleasant thing to do. From other side, if it's important, people would have bothered. So you would say it probably has bad ratio of difficulty to importance. One of the reasons probably that in most of the lower dimensional applications where these terms are very important, like, for example, computation of scalar potentials, the nonlinear completions are somewhat less important. In a sense, okay, if you do 4-point calculation and you see linearized gravity from general covariance, you know that this you can replace it by Riemann tensors. You don't know such things about B field, about dilaton, and so on and so forth. When you compactify, the B field and metric do not sit in the same multiplet anymore. Okay, so in some ways, it's you kind of hide behind other things and you do other techniques, but knowledge of these terms, nevertheless, would be very important. And okay, given that now we have a whole new formalism which somehow fuses the metric and the B field, of course, it is natural to ask, is it going to be helpful? So let me just start with a very, very brief review. So in type 2 theories, this couplings, or what's known, and as you see, it's only R's here so far. So these R to the 4 terms, they appear at 3 level, both in type 2A and type 2B. Actually, it's identical. And there are 2 structures which appear, sort of tensor kinematic structures. T8, so-called, and epsilon. Well, I don't need to explain what epsilon tensor is to you. So T8, if you wish, here is a definition. It's some tensorial structure that if you contract it with 4 powers of metric, it will give you some particular trace combination. The way it appears, it is also related to just product of 4 gamma 2 matrices. Okay. At one loop term, it's a very different size of GSO projections. Type 2A and type 2B diverge, and type 2B has, as you could guess from S duality, a similar coupling to 3 level, so that's the plus sign, and type 2A has an opposite sign. You pay the price for flipping by having a different new coupling in type 2A theory, which is the kind of an analog of Green-Schwarz for type 2 theories. It is related to anomaly cancellation. So in this case, it's not the space-time anomaly, but it's the anomaly of M5 brane or NS5 brane. Now, it's also been known, I mean, at linearized level, the calculations are going back to Gross and Sloan for 3 level. It can be also checked for 1 loop, that if you are doing 4-point calculations also with the B field and dilaton, actually what you see is, again, linearized version, the part in blue, of Riemann computed from connection with torsion. So, of course, you don't see H squared, okay? But you see these things. And the powers of dilaton appear in such way that when you go to string frame, they just disappear. You scale them away, okay? So this has been known for a long time, I mean, especially for 3 level. And if you wish, here is a problem, as I said. So here, I don't even bother to write linearized gravity. You can just straight away write Riemann. Okay, you can write double h. You have no idea whether the things are going to complete to h squared. Okay, there is no principle telling you that it's going to happen. And in fact, it does, but it's not the full answer. Okay, so two things to which I will return in this talk is that, okay, there is some law that, okay, when you stare at these things, you can say that, oh, I can rewrite everything in terms of two different n equals 1 super invariants, and then everything which appears in the effective action is some kind of combination of these two. Okay, and then there is another thing, of course, if I find a type 2 decoupling, which is all given both at tree level and one loop, okay, and if I find an SL2 invariant object, and in this case there exists this automorphic function, which the Eisenstein series, which looks exactly what you would be expecting. It has a, if you do an expansion in powers of dilaton, it has a tree-level term, one loop term, and then non-perturbative contributions. Okay. Okay. So this is the background. This is the kind of state of affairs. As I was saying, the 4-point functions have a long history, and then somehow it stops. Well, actually, in type 2a context, in type 2 context, it probably took order of 10 more years to go from tree level to one loop, but then it's another 20 years. So I'm talking about these things, and no, you don't find this in the literature. Okay, so it is the subject of this talk. And as I said, generalized geometry can just offer some timid mumblings about how it might or might not see some of these structures. Okay, I was planning to skip this one, but maybe I will do it for Niels. So one way of seeing generalized geometry without generalized geometry is something, I mean, you all know, Lishner-Ovitz theorem. So Lishner-Ovitz theorem is just a beautiful thing. Here it's written. It's also one of the magics of Riemannian geometry. That if you take a Dirac operator and you take covariant derivative, there is a quadratic combination of this difference of squares, which is purely tensorial. Okay, so now if you are given this, the theorem was generalized in the context of index theory. So people asked, okay, what would be, how would we compute local expressions for, again, global expressions don't matter, meaning if you were to integrate, if you are interested in number of zero modes, that's the magic of characteristic classes and index theorems, is that you don't worry about choice of connection. But if you ask about local questions, and the connection is important, so people asked, what if you are given a connection with torsion? How would you write the index in terms of local polynomials? Okay, and the first step was, please start by finding a combination of operators which gives you a tensorial expression. So what you have to do is going from Dirac operator to covariant derivative. And you do it by saying, oh, I will find a difference of squares of two operators, which is tensorial. And clearly, because this works for Levi-Civita only, the Dirac operator cannot be gamma trace of the covariant derivative. It has to be something else. And if you check the condition for tensoriality, you find the coefficients here, which actually correspond, this alpha and beta. So there is a relative factor of 3 there. And this exactly is the factors, are the factors, which appear in the variation, SUSY variation of Gravitino and Dilatino. Okay, so this factor of 3, at least in my personal life, is the most important factor of 3 I've ever seen. I challenge you to find a more important one. Okay, notice in all this story, there is no dilaton. If you try to do something naive and say, oh, I know the SUSY transformations, I can just take the SUSY transformations with the dilaton and try to plug it in, you immediately run into problem. Okay, so this is, if you wish, and there the treatment, for the real treatment of it, you have to go to generalized geometry. It sounds a little bit absurd, but between the metric and the B field, I don't even need generalized geometry. Here, I have a generalization of Lishner-Ovitz theorem due to bismuth. So it's the dilaton which forces me to go generalized. Okay, but if you start correcting these operators by sort of more and more terms, it gives you some way about thinking about quantum corrections. But for now, I just want to show you the corrections themselves. Okay, so here is the summary of result. I mentioned already about 4-point functions. Okay, there is an extra column, and I'm showing that actually for 4-point functions, there is also some calculation involving Ramon fields, which I will be needing further in my talk. Okay, so this all has been good and known. So here is what you see beyond starting from 5 points. Okay, so clearly, I mean, and okay, I probably should say it. Yeah. Okay, or maybe you should read the caption to the title. So I am, when I say, let's say R to the 4, I mean R to the 4 with connection with torsion. That means if you do the expansion, of course, it also contains higher point function contributions. Okay, just like Hilbert-Einstein contains all orders in gravity. So what the terms that I'm writing explicitly, these are the terms beyond that expansion. Okay, new terms which appear only, let's say, at 5 points. Okay, and they do appear. So at one loop, the situation is kind of fairly tame. Okay, you have just sort of some new terms, and I will just show in the next transparency that why this is fairly tame. It's a big surprise that at 3 level you get a whole zoo of them. Okay, so here is the one loop. The one loop is nice because you can arrange your calculation by sectors. So there are even and odd sectors, and 3/4 of the theory, and this is a claim which I believe goes beyond 5-point functions, that it's all order claim, that in the even, odd, even, odd, 3/4, all you need to do is replace the connection by connection with torsion. This completely captures the B field. So all the surprises, all the new things sit in the even, in the odd sector. Okay, which again, if you know the history a little bit, it's the kind of, it has always been the nastiest one. This is the one which at 4-point function actually vanishes. So it took longer time to fix it. For example, the relative factors, even though people believed that the terms are there, and they were originally fixed by things like dualities rather than direct computations, because it would require you to go to 5-point functions. Okay, so we start seeing new things at in the odd sector at nonlinear order, and there are sort of new kinematical structures which do not appear just in standard expansion. So it's not just a matter of having wrong coefficients. You really start seeing new kinematics, which might make you wonder, okay, if this kinematics by itself is kind of meaningful. Now, if you go to 3 level, you see, there was a guess originally. Actually, something which prompted our work was sort of a guess of a new term in a 3 level calculation. Well, I should say probably more than a guess. So people took the known corrections to moduli spaces of hyper and vector multiplets and tried to put all the new things we knew about, let's say, one loop couplings into it. These corrections were obtained mostly by kind of string theoretic techniques. But then they asked, okay, can we get it from the reduction of the known terms? And somehow the claim was, oh, look, the one loop part is all good, but the 3 level part is somehow, as it stands, is incompatible with supersymmetry. It would require, in order for all these cancellations to work in the internal part, in the Calabi-House, to match the 4-dimensional n = 2 results, one needs somehow new kinematics. And what they came up with is, with this term, it's written out explicitly here. Okay, if you know a little bit, you see the way the contractions go and stuff, you see that this kind of thing, again, it's not H² term, which would be sitting inside one Riemann. Inside one Riemann, you would have to swap the mu's and one of the mu's with one of the nu's. Okay, it's a completely different kinematics. Now, if you are doing the things from sort of low energy, low dimensional point of view, of course, you should be saying, oh, we need this term and all sorts of terms which we do not see in the reduction, because the terms which in the reduction context contribute to zero. Okay, but of course, it's hard to generalize the zero somehow. And when you go into direct calculation, yeah, you find, okay, so you find another kinematical structure which is just exactly like the one which was in type 2 at one loop. This guy, it has a different coefficient. Okay, and then you find a bunch of new terms. You can write them explicitly. We did. We realized, okay, the best we could do was to arrange them just simply in a basis of our cube combinations. I mean, group theoretically, there are just 8 independent combinations. So 6 of them are antisymmetric in triples of indices, and then there are 2 which are antisymmetric in 5. So you write 8 independent terms, you have a full basis, and then you can write things in this basis and have a set of coefficients of D. And we couldn't find, as it's written here, Jim and I, we stopped at this because we couldn't find any nicer rewriting. So we thought, okay, this is the best we will do, and one day maybe there a better person will appear who will do that. In fact, paraphrasing Lenin, I can say such a person exists. His name is Andreas Schaffner, and this is what he realized, that yes, you can by changing this coefficient and reassembling the terms, you can actually write everything else in terms of some, well, known tensorial structure, which is like T18, which has a product of 2 gamma 3s and bunch of gamma 2s. But this object, it does appear in the vertex operator expansion in the superparticles. Okay, when you are reducing 11 dimensions to 9. So indeed, you can do better, of course. I mean, from point of view, okay, I tell you how these things are related in terms of gamma matrices, but you wouldn't really call this a good geometric understanding. Okay, so one thing that you probably should retain from my original transparency, going back, you see that 3-level and 1 loop are very, very different, starting from 5-point functions. Both at the level of coefficients, these terms, but also at the level of, so this against this. But at the level of appearance, really new kinematics, different kinematical structures. Okay, so differences of 3-level and 1 loop, of course, lead to some immediate problems. So notably, you can realize after playing and staring and stuff that this claim about 2 different super invariants cannot possibly hold. So the best you can hope for, and part of it, of course, is a guess, is that, okay, you have a single 3-level super invariant, which can be promoted to super invariants both in 2A and 2B, and you have 2 different 1-loop super invariants at n equal 2, which combining with different GSO signs, then you can promote either to 1-1 or to 0 in 10-dimensional sense. So the theories with 32 supercharges, so 2A or 2B super invariants. Okay, but once more, sort of any understanding of this kind of claims from point of view of geometry is not very obvious. Okay, so here is another thing. I collected everything we have for type 2B theory with signs and everything. You stare at it and you ask, how does this go along with SL2? Okay, because this was another kind of thing that what we knew all this time, that I started my talk by saying, oh, if you look at 4-point functions, the 3-level and 1 loop in type 2 look exactly the same. And that's why you can take the same kinematical structure and multiply by something which is SL2 invariant. Okay, so different kinematical structures means you have to go to invent new things. Okay, first thing you do is everything is written in terms of H field, but you write it in terms of G, in the standard object which appears in type 2B, which is a complex field made out of F and H, and you realize actually that starting from 5-point functions, you can have U1 violating terms. Okay, so what you have is that the kinematical structure actually transforms with some U1 charge, but then instead of an automorphic form, you need something which transforms with an opposite side charge. Okay, so the net thing is still neutral. And okay, we are kind of lucky because when we are looking at just 5-point functions, so there is an understanding that this maximally violating U1 amplitudes, which are the nicest, are sort of the U1 charge is related to in this fashion. It's 4 plus k. So since we are talking about 5-point functions, the only U1 violating terms are maximally U1 violating. Okay. All right. So if you look at this automorphic form, which is written, the expansion is written here, you know that it is kind of sits in a top of a tower, and by some kind of recursive or descent relations, you can actually get a host of forms which transform with the weight k. Okay. One way or another, the net result is this. You can put everything together, and as I said, since you have at most one U1 violation, so only F1 appears. But if you look at higher point functions, of course, you would have higher these Fn functions. Probably the biggest surprise of this calculation was that there is a CPO term. See, in 2B, there is no anomaly, there is no chiral membrane, 5-brane. So, of course, it shouldn't be anomalous, but the way it's written, so G wedges with something which is exact. So this guy does not, I mean, everything here is gauge diffeomorphism invariant individually. So no, it doesn't give rise to any anomalies differently from the 2A counterpart of it, okay? Because I started from a difference of characteristic classes, which is an exact term. But yeah, its appearance has been somewhat surprising and somewhat, but I mean, it has been also tested in all sorts of setups that it's required by supersymmetry, by dualities and everything, that if you do nonlinear tests, everything seems to be compatible with, or actually require the presence of such a term. Okay, now in the remaining of the time I have, I mean, I will try to move towards some sort of attempts of geometrization, and this will not be generalized. It's the good old F theory, or if you wish, if you call F theory also generalized geometry, it would be your right. So it's a very simple kind of dumb observation. Yes, the way we should be thinking about F theory is putting M theory on circle or elliptically fibered Columbia-Gauss, whatever, and taking from 9 dimensions a new decompactification. So M theory on T2 would have 2 different decompactification limits. One would be just boring, going up along one of the circles that you came down to. Another is some kind of diagonal circle in T2. It's a 0 volume limit, and that decompactifies you to 2B. Okay, it preserves the complex structure of the torus, so you preserve your SL2. One way or another, see, by doing so, you recover an action of gravity coupled to a complex scalar. So this is the dilaton axiom. You can do a completely formal exercise, which in some ways was done in the original paper of Green, Shapir, Yao, and Waffe and Yao on cosmic strings, that you can see a scalar and the complex scalar coupled to gravity as pure gravity 2 dimensions higher on a fixed volume torus. Okay, so at 2 derivatives, there doesn't seem to be okay. You can do one or the other. The question is, okay, what about R to the 4th? Now, the M theory point of view on these couplings is rather well established. Again, you can do similar exercises. There you see the appearance of this Eisenstein series as coming from summing Kaluza-Klein modes on T2. And yes, it does have a decompactification to B limit, which gives you the R⁴ couplings that I was mentioning. Of course, there is no word about kinematics here. Now, you can also look at just 4-point functions, generalization of Gross and Sloan, but with Ramon-Ramon fields. And there you see some part which is perfectly predictable. You see T8, R⁴, as you should. And then you see something which involves the scalars. And that's, again, has the same kinematics. And then you see a bunch of new stuff. And this bunch of new stuff looks absolutely disgusting. I mean, it's not any kind of nice expression. So, ugly. Here, you try the simplest thing possible in order to make it pretty. You say, look, and once more, it's a guess. It either works or it doesn't. There is no real justification for it. Sort of a belief that F theory should geometrize things. So you say, look, can I just take this metric, which actually worked for the 2 derivative couplings, and do the same formal exercise? Just write a term like this with the all known kinematics with the T8s, except let the indices run longer range. Okay? And I do, please, do not get an impression that I am claiming that there is a 12-dimensional theory. It's just a purely formal exercise. The volume is fixed. There is no Lorentz or anything. Okay? So you do this exercise, and this guy, when you reduce it, of course, it will give rise to 10-dimensional T8 and the things contracted into it, but a bunch of new stuff. And that bunch of new stuff matches on the nose this ugly kinematics that you get from string calculations. So yes, F theory nicely geometrizes the 4-point function interactions. And you can push it further and actually try to write something which also involves the epsilon sector, which vanishes at 4-point level after you reduce it. I mean, you can milk this result in some ways. For example, you can get corrections to Kähler potential, which previously people were arguing starting from n=2 and going to n=1, essentially claiming that, oh, it's the same potential. And no, the answer is no, it's not the same potential. You do get a correction. And in all the cases that had been tested, the previous cases were tested in the literature, there were in toroidal orbifolds model, and these things depend on triple intersection of 7 branes, which such things just simply do not arise in the orbifold models. So you do get new physics, but the big questions are, okay, fine, we can rewrite these things. We can have some guesses, for example, about maximal U1 violating terms involving the fluxes and the metrics only. But there is a lot of problem with any kind of geometric interpretation and putting it in some kind of F-theory friendly framework. And once more, the dilaton is just a very complete mystery. You see, the big difference between the B field and the dilaton is that the B field has parity properties. Every single coupling in type 2 should be even in powers of G. We don't have such things in with dilaton. So, for example, a coupling of the type like this, you see, I have odd number of dilatons under derivatives, which means I cannot really, I mean, the only way of making U1 neutral expressions is having a field and its bar. So if I have odd number of dilatons, which I promote into P's, I cannot have equal number of them to distribute the bars and non-bars equally. So this is what we are currently trying to check, and hopefully we'll be able to check. But once more, just in the spirit of Niels' talk, dilaton is a bigger nuisance than you think it should be. I will finish here, and differently from Niels, who had a big list of questions, I just have one simple one. You know, can you people do something about it? Thank you.
Thank you very much, Ruben, for a very nice talk. Are there any questions in this audience? Niels has one.
I was just wondering, these higher form Eisenstein series, like the Fn with F with n not equal to 0, do they also satisfy some non-renormalization theorems? Like if you expand them to...
I don't think there is any... yeah, it's a hard question. I think the only non-renormalization normally is at one loop. It's yeah, so here you are just matching SL2 properties.
But okay, yeah. Maybe I didn't say it. Take F1. If you make a weak coupling expansion, what does it look like?
It looks exactly like F0, meaning it still looks like 3-level, one loop, non-perturbative. They all look similar, it's just the differences in coefficient. So if you do the expansion, that's why we could actually, you take different terms and you just have two linear combinations, but you are not creating any new strand, like you don't, by introducing F1s, you don't create two loop terms or stuff. No. Yeah.
Thanks a lot.
Further questions? Peter has one.
It's more a general question. Do you think or do you believe that these higher order terms in gravity can be obtained by double copying Yang-Mills?
KLT relations, yes, absolutely. So everything which has with two good old double in a sense of KLT, I believe it. Lots of other doubles, I don't believe it. I just go for record, gratuitously again.
Okay, maybe we should look at the online questions, see if there are any. Yeah, go ahead.
Hello, can you hear me? Can you hear me? No.
Vaguely.
Vaguely, okay. Sorry, I'm Luca Martucci.
Hi, Luca.
No, you cannot hear me, okay.
I can hear you, Luca.
Okay, sorry. So my question is, what is the precise interpretation of your effective action? Is it a Wilsonian action defined some cutoff scale fixed by the string scale, or it has some other interpretation?
No, I would say that's the one.
But so in that case, should you also take when you do the matching with the string computations, should you also include the
string computations? I just didn't show you.
Okay. Just to,
yeah, so it's
you have to.
As I was telling you, for example, some terms were guessed from supersymmetry, or not guessed, conjectured or postulated from supersymmetry in order to match the reductions with the known results on quantum corrections. But every single thing which I showed comes from a string calculation.
Okay, I'm just asking if in the matching you also include one loop terms coming from the two derivative terms, which may compete with a higher derivative, with a 3-level contribution from the higher derivative terms. And I was just curious about it.
Yes.
Okay.
Thanks.
Thank you.
Can I ask a question too?
Sure. Hi, Wolfgang.
Hi, Ruben. Nice talk. Actually, just to point out, in the late 90s, I was working with Stefan Stieberger on F2-4 couplings in 8 dimensions, also from F theory. So there is a geometric computation for some terms in 8 dimensions. And there was a kind of mysterious geometric structure behind it, which we never could really figure out. Namely, it looked like as if there would be a hidden 5-fold in the game. So if you do mirror symmetry on this 5-fold, then you reproduce certain couplings in 8 dimensions.
Oh, thanks a lot. Yeah, as I said, I'm sorry, there is a whole lot of literature which is absolutely not on this transparency, but I will definitely have a look. Thanks.
Yeah, I think that's it. So let's take Ruben one more. And let's reconvene in say 25 minutes in here.
You want to turn this off or? Okay, I'll just hand it over to you.